So this video is going to be about Bernoulli's equation, and we'll be looking at exactly what is Bernoulli's equation and some typical applications. So I'll cut straight to it. The following is Bernoulli's equation as applied to a 1D flow. The first term, P, is pressure, or sometimes called static pressure. The second term, rho GH, is the hydrostatic pressure. The third term, a half rho V squared, is the dynamic pressure, and this all equals P naught, which is the total pressure. Now, you have to be careful not to mix up the static pressure, the P, with the total pressure, the P naught. The static pressure P is the pressure that the fluid is experiencing, and it's the pressure that you're interested in. For example, if you're looking at pressure tables or steam tables. Also, what's quite important is that P naught is a constant and is occasionally referred to simply as a constant instead of the P naught itself. So the reason we learn about Bernoulli's equation is that it's a keystone for more advanced fluid dynamics. It also introduces the relationship between velocity and pressure, known as Bernoulli's principle. That's a really important concept in fluid dynamics. And it conveniently follows on from the hydrostatic equation that we've learned about previously. The only change from the hydrostatic equation is that there is a new dynamic pressure term, the half rho V squared. Very common example or exam question that you might get are what I refer to as Bernoulli pipes. So they're very simplified pipes, and they're popular because you're forced to use each term in the Bernoulli's equation, and so you can get familiar with what each term is doing in the equation. So typically you're asked to solve at single points along the pipe, and this doesn't allow understanding of how the pressure and the velocity are evolving as the water is flowing through these transition points. So what I want to cover here is the evolution of the velocity and the pressure as you go through these Bernoulli pipes. So Bernoulli pipes, you'll see two types of transitions, which will be a transition to a change of height, or it will be a transition to a change of cross-sectional area of the pipe. So either the pipe is getting wider or narrower. So the first transition that we're going to look at is the height change. And during a height change, the velocity is going to stay constant across all points in the pipe. And this is going to be due to the conservation of mass, that any fluid that enters the pipe must leave the pipe. And so long as the pipe isn't changing cross-sectional area, it must be leaving at the same speed at which it's entering. So as the pipe changes height, what we're going to see is a change in the hydrostatic pressure, or the rho GH term. And in this case, the pipe is decreasing in height, so we'll see a decrease in the value of the rho GH term. Now, velocity is constant, as I've already said, which means that the half rho V squared term is also going to be constant. And as I mentioned at the beginning, P naught, total pressure, is constant. So, in order to balance the equation, if rho GH is decreasing, i.e. hydrostatic pressure is decreasing, then the static pressure, the P, must be increasing in order for the equation to stay valid. So, as I said previously, and as this graph shows, the velocity is going to stay constant at all points along the pipe. So actually, an interesting side point here is that Bernoulli's equation assumes the flow is incompressible. So as a bonus, you might like to think about what is actually going to change to Bernoulli's equation in this case if the flow were compressible. So as for the pressure graph, what we see is a linear increase of pressure with depth because the hydrostatic term is linear. So the pressure, if the hydrostatic term is decreasing linearly, the pressure term must be increasing linearly as well. Next, we're going to look at constrictions, and the opposite of constriction is an expansion. I'm not going to look at expansions because it's effectively the same maths in reverse. So a constriction is going to affect the half rho v squared term, and the reason why that is that as the pipe constricts, the velocity is going to increase. Effectively, due to the conservation of mass, you're forcing the same amount of fluid to go through a smaller space, so it needs to move quicker in order to maintain the constant mass flow rate. So the velocity is increasing. That means the half rho v squared term is going to increase proportionally to the square of the velocity. The rho gh term is a constant again. The p naught term is a constant, which means that the pressure has to decrease at a constriction in order for Bernoulli's equation to stay valid. So this is known as Bernoulli's principle, that an increase in velocity leads to a drop in pressure, and this is going to be discussed in detail later because it's really important. So as I said, at a constriction, the velocity is going to be increasing. In this case, the constriction is linear constriction. The velocity will be increasing linearly, as in a straight line. The dynamic pressure is therefore going to be proportional to the square of the velocity. So it's going to have a parabolic shape. And if the dynamic pressure is increasing according to the square of the velocity, the static pressure, P, has to decrease according to the square of the velocity, or according to the dynamic pressure term as well. So as you can see in the graph, the velocity has a linear increase, the pressure has a parabolic decrease, and that's simply to balance Bernoulli's equation and to make sure that it remains valid. And that's all I'm going to cover in this video. So as I said before, Bernoulli's equation is really important. It demonstrates Bernoulli's principle, which is this decrease in pressure due to an increase in velocity. And because this Bernoulli's principle isn't so intuitive, we're going to do more videos on the topic. Thank you for watching, and we'll see you next time.